Here we're going to do another indirect proof using a proof by contradiction, except this is a more difficult proof. This proof is a little bit harder to see the direction to go, and so I'm going to show you how useful breaking a problem into cases can be. Okay, so this is Module 4, Video 3. And let's recall how we do a proof by contradiction. We want to suppose or assume that whatever we're trying to prove true is actually false. So we want to suppose the negation of our statement. In this particular problem, we are going to be using a universal conditional problem. So to prove some universal conditional problem statement, we want to suppose its negation. So we want to suppose that there exists an element of our domain such that our initial statement P of x is true and Q of x is false. Like that. And from that, we want to derive a contradiction. Right? If we can find a contradiction, then we can conclude that our original statement must be true. Okay. So in this problem, we want to prove that for any integer n squared minus 2 is not divisible by 4. So the very first thing I always do when I do one of these proofs, maybe we can just call it step 0, I think I've said that before, is I want to write this out formally. So we say for any, that's the same thing logically as for all integers n. Ooh, but now what's my if then? Right? I don't know quite how to turn that n squared minus 2 is not divisible by 4 into an if then. So here's an opportunity to use the trick we've learned, which is instead of including that n is an integer in the domain, I'm just going to say for all n regardless of domain, if n squared minus 2, if I'm going to say in the if n is an integer, then n squared minus 2 is not divisible by 4. Right? Now, I can put my negation down. It's also part of step 0. I'm going to negate this statement. I'm going to say there exists an n such that n is an integer, and now remember I want the opposite of this part over here. So n squared minus 2 is divisible by 4. Okay, so once I've figured out how to write my statement formally and what its negation is, now I can begin my proof. And step 1, we want to suppose the negation. So I always say suppose not, because remember, step 0 isn't really part of our proof. So we're given that we want to prove that, and I'm going to say, well, suppose that's not true. Suppose not. That is, suppose. Now we want to suppose the negation. And while I think it's much easier to write the negation out if we first convert this, the statement to a universal conditional statement, I'm going to notice that this right here doesn't really add a lot. So I'm going to compress that and say, suppose there exists an integer n such that this last part is true, which is another way of saying and that part is true, such that n squared minus 2 is divisible by 4. Well, what does that mean? Divisible by 4. If you recall, divisibility means it's equal to whatever number it's divisible by, in this case 4, times some integer. So we want to show, suppose that there exists an n is in the integers, such that n squared minus 2 is, let's rewrite this. Squared minus 2 equals 4k for some integer k. That is the definition of divisibility. So we're going to suppose this is true. This is step 1, and now we want to demonstrate a contradiction. But it may not be entirely clear what that contradiction is. Right? I'm going to suppose this, but how do I go about showing that that leads to a contradiction? I could try to factor the left side maybe, or I could divide both sides by 4. The reason I can work with this as an inequality, because you recall a previous video I said that you never want to suppose equality if that's what we're trying to prove, is that at the moment we're not trying to prove that these are equal. We are supposing that they are equal. And so there's a difference. I'm not trying to show them equal. I am supposing that it is given that they are equal. And if it's given, I certainly can set it up as an equality and simplify from there. Okay, so it's kind of a subtle distinction. Am I showing that they're equal? If I am, I don't want to assume they're equal. I want to start with one side and deduce the other side. But if it's given that they're equal, then I can use that fact and simplify from there. So I could indeed divide both sides by 4 here, except that I don't know what that would give me. How would that help? In a situation like this, where it's sometimes hard to figure out where to go, one possible approach is to divide this into cases. So we're saying there exists some integer, right, with this property. Well, integers can be broken into a couple of different situations. We could be talking about negative integers, positive integers, and 0. Right? All integers are either negative, positive, or 0. So I could break it into those 3 cases. Another way of breaking this into cases is we could say, well, all integers are either even or odd. Right? Whenever you break something into cases, you have to make sure that every value you're considering, in this case all integers, fits into one of your cases. So this is a way of doing cases, the negative, positive, and 0. And this is a way of doing cases, breaking them into even and odd. Since divisibility kind of looks like even, let's give that a try first. So I'm going to see, let's see if it helps. To see what happens if n is even or odd. Okay, and so this technique, I'm going to break it into cases, and I'm going to look at the case where n is even, and I'm going to look at the case where n is odd. So okay, so let's move to the next page. And once again, I'm going to start at the top. I'm going to grab my supposition. And which is right here, right, step 1. I'm going to copy that onto the next page. So, actually I'm not. Instead, we're going to jump straight to the cases. So we're going to look at the two cases. But remember, what we're supposing is that n squared minus 2 is equal to 4k for some integer k. Let's do it that way. Suppose n squared minus 2 equals 4k for some integer k. Now, case 1. N is even. So we're sort of supposing this. This could also be written as suppose n is even. Well, what does that mean? Well, if n is even, then n equals 2q, because we need to use a different variable. I can't use k again. For some integer q. Okay, well then n squared minus 2 is going to be 2k, or 2q, excuse me, squared minus 2, which we can rewrite as 4q squared minus 2. And remember, by assumption, we know that n squared minus 2 is equal to 4k. So, since n squared minus 2 equals 4 times k, let's play with this. If we know that n squared minus 2 is equal to 4q squared minus 2, so I'm going to substitute that. So 4q squared minus 2 equals 4k. Let's see if we can solve for some of these variables. So I'm going to subtract 4k from both sides. Right. And now it looks like I can pull a 2 out. Actually, before I do that, instead, I think that's going to be harder. Instead, let's move the 2 to the other side. So I'm going to add 2 to both sides. Because now I can pull a 4 out over here. So I'm going to move up over here, and I'm going to say this is equal to 4 times q squared minus k equals 2. Now, how did I know to move the 2 over? I played with this. Right? I'm showing you the end result of my proof. When I sit down to prove something like this, I scribble and I try this and I try that. Right? It's not going to be this straightforward when you're doing it yourself, and you shouldn't expect it to be. Okay, now that I have it broken up like this, I'm going to divide both sides by 4. So we get that q squared minus k equals 2/4, which is the same as 1/2. Right? And it may seem a little subtle, but this is actually where we can find our contradiction. Because I'm saying that q squared minus k is equal to 1/2. But what do I know about q squared minus k? Q squared minus k, q is an integer and k is an integer, so this should be an integer under integer closure properties. But it's not. It's equal to 1/2. There's our contradiction. There's our contradiction. Right? Because it should equal an integer due to integer closures, but it's not equal to an integer. So we've run into a contradiction. Well, what does this contradiction mean? Now we've got two assumptions going on, right? We've got our big overall assumption that n squared minus 2 equals 4k, but we also have this newer assumption. We're supposing that n is even. And this contradiction is going to sort of cancel out the most recent assumption. So this contradiction means that n cannot be even. So therefore, n cannot be even. And the reason it just cancels that one out is because we don't know anything about what if n is odd. All we've shown is that n can't be even. That's what our assumption was working with. So this statement up here, our initial suppose, could still theoretically be true if n were odd. So that's what we need to look at next. So recall, we are supposing that n squared minus 2 is equal to 4k. Is that right? Yeah, for some integer k. Okay, now we're going to look at case 2. N is odd. Or again, we could write this as suppose n is odd. Okay, so what does that mean? Well, if n is odd, then n equals, we could reuse the q because we're sort of done with the q here. We've finished with it. But just to be clear, I'm going to use a different variable. N is 2p plus 1 for some p in the integers. Well, so let's plug that in. So we have n squared minus 2 is going to be 2p plus 1 squared minus 2 by substitution. I haven't been great about writing that in. I didn't put it in here either because I knew we were going to run short on space. I'm going to run short on space either here too, so I'm not going to put it in. But if I was doing this on paper, I would write in the reason. How do we know this is this part? Well, I know it because of substitution. We're substituting in the value of n. And what can I do with this? I can factor it. And if you factor this out, you're going to get that this is 4p squared plus 4p minus 1. And again, I'll leave that algebra to you. But that's through factoring. And we know that since n squared minus 2 is divisible by 4, we know that we can substitute that in for n squared minus 2. So we know that 4p squared plus 4p minus 1 is equal to 4k as well, because that's really what we're saying here, that this n squared minus 2 is divisible by 4. We're saying that it equals 4k, which is indeed what we put up here in the top. Okay, so this equals 4k. I'm going to kind of play with this like I did before. I'm going to move the 4k over by subtracting it from both sides. And then I'm going to move the 1 over. All right, and again, I get here just by fiddling with it. Now what can I do? I can pull a 4 out. And once again, I can divide both sides by 4. Right there. And once again, we run into the same problem, right? We have something that is the product, the sum, and the subtraction of integers. So it should be an integer, but it's not. But it's not, so we have a contradiction. And we found a contradiction, so once again, our most immediate supposition cannot be true. So therefore, n cannot be odd. So, we said to suppose that n squared minus 2 equaled 4k, and then we said that n cannot be even. Right, we said that back here, that n cannot be even. And then we said n cannot be odd, putting these together, since n cannot be even and n cannot be odd, n cannot exist. Right? Because there's no other choices. When we broke the world into two cases, we said n is either even or odd. There's no other options. There's no third option. So we said that an n existed such that this statement was true, and then we found that n cannot exist. So there's our contradiction for the second part. Right, and this contradiction lets us conclude that this supposition was wrong, which means that our original statement, which if we look back a few pages, our original statement was that for all n, so this is right here, for all n, if n is an integer, then n squared minus 2 is not divisible by 4. We know that that must be true. Therefore, since its negation is false, our original statement is true. Okay. So the rest of this is just a typed up version of what we just did. So I will let you go through that. I'm going to go back through slowly so you can pause on them. I'm a little too fast. So if you would like to pause and look at the formal write-up, you can. But it's really just the same thing as what we just went through. Right, and this is really important as well, that if you use a proof by cases, so this was a proof by contradiction using cases, breaking the problem into cases. This is a really powerful technique, but you really need to make sure that all your cases are covered, that you don't leave anything out.